Today we're going to talk about functions, but before we get there we need to develop some tools. The basic idea of a function is you have some set of inputs, and then once you use the function on those inputs you get a set of outputs. Okay, but before we need to develop some terminology to get there. Again, the set of inputs, or independent variables, constitute what we call the domain of the function. So for example, we could have some inputs, say like 0, 1, 2, -5, and then we can even have abstract objects such as like a dog. Okay, and then we have some relation that takes these set of inputs and we get an output. And those outputs, or dependent variables, the set of all those constitute what we call the range. So we could get something out, say -10, 20, +2, 9, and then we could have a cat. Okay, so for example, under this relation, we can define it however we want right now. 0 could go to 2, and 1 could go to 20, 2 could go to a cat, 5 could go to 9, and then the dog becomes a -10 somehow. And so after we do this, after we put the inputs into this relation, we get the outputs, and mathematically we can, instead of doing all this, we can use a shorthand and say, okay, well, we're going to list a domain value, comma, the range value inside a set of parentheses. This is called an ordered pair. So for example, if I use the domain value 0, under the relation, the corresponding value we said was 2. Okay, so I can list it like that. And now in particular, if we restrict this relation so that only for each input we only have one output, then it'll be a function. So an example of when it wouldn't be a function is if we had 0 going to 10 as well, because 0, one domain value, is going to two different outputs, two different range values. Okay, and this is one way to represent a function analytically with the use of sets. We can also look at the use of functions graphically when we obtain the graph of a relation. And the test that we use to determine whether or not we have a function is called the vertical line test. So if I take my vertical line here, and if I pass it through the graphs of these two relations, if it intersects the graph of the relation more than once, then it will not be a function. So I'm passing this vertical line through, and it's only going to hit once. So this on the left is a function. On the right, now I'm going to begin, and as soon as I get to 1, or actually before then, I see that the vertical line intersects the function at two different places. Now, the reason I have the lower half is in red is it's actually a second function. But if we just restrict the function to that first curve, then it will be a function. But as it is shown, this is not a function. So again, second way to represent a function, graphically. Third way, and probably the most common way that we think of a function, is through the use of an algebraic expression. And so this says f of x, or the function evaluated at x, is equal to 3x squared plus x minus 4. Okay, and then again, we have probably seen this before, but just as a refresher, if I have f of minus 3, this says, well, instead of x, wherever x occurs in my function, I replace it with a minus 3. So I'm going to have 3 parentheses, and I'm going to use a parentheses here and put -3 inside and square that, because I want to make sure that I keep the sign with the x. Okay, and then similarly I'll have a plus a minus 3, and then a minus 4 on top of all that. So this is going to be 27 minus 7 gives me a total of 20. Now the second one, I'm going to do the same idea. So wherever I have x occurring in my function, I'm going to replace it by x minus h. So I'm going to have 3, and then open a set of parentheses, and now instead of x, I have h minus x. So h minus x squared plus, and then replace the x with x minus h minus 4. Okay, that's fine. If you want to be a superstar and go that extra mile, expand it out and you'll get 3h squared minus 6hx minus plus 3x squared, and then plus h minus x minus 4. Okay, again, just a little bit of algebra there. Okay, third way to represent a function, algebraically. Last and final way that we're going to study is through the use of a table. Okay, so we have a context here. We have a biology lab talking about rate of growth of bacteria at various temperatures. Temperatures given in Celsius. Rates are given in milligrams per minute. Okay, so part A, what are the independent and dependent variables? Okay, so we need to think in this context, what are we saying varies? The thing that is varying here is not the temperature, it's actually the rate. So the rate is deep, well, we're varying the temperature, yes, but the rate is actually what we're saying is hopefully depending on the temperature. Okay, so I'm just going to write, rather than write it down here, I'm just going to say, okay, the rate is our dependent variable, and then our temperature is going to be our independent variable, what we control. Okay, part B. Does it appear a function can be used for modeling purposes? Well, let's see. Well, we know that a function, for each input, there can only be one output. Well, it looks to be that case. We're not saying that one domain value goes to two different range values. So yes, in theory it could. We actually have to get an exact model and do some more modeling procedures with it. But for now we can say yes, no domain value goes to two different range values. Okay, and now this last one, this might be a little something new to us, but it says, okay, so if we know the temperatures given in the table, we want to estimate the rate of growth of the bacteria at room temperature, and we're going to call room temperature 22 degrees Celsius, and then we're going to use this by linear interpolation. Okay, this is something new. It's not a big grandiose idea, it's just proportions. Okay, so I know data at 20 degrees Celsius and at and at 30 degrees Celsius. Okay, at 20 degrees Celsius, it's growing at a rate of 2.1 milligrams per minute, and at 30 degrees, it's at 0.3 milligrams per minute. Okay, so at room temperature, and well, 22 is going to be somewhere in between here. And actually, we don't know that value. That's what we want to determine. So R is going to be our unknown. Okay, well, let's just look at the change here. And again, we're just going to, calculus is all about change. We have to get into that mindset. So from 20 to 22, that's a change of positive 2. Okay, and the other thing we know is from 20 to 30, that's a change of positive 10. Okay, now we have to, whatever we do on this side for proportions, it's going to be the same on this side. So this is some unknown change x, and from here to here, from 21 or from 0.21 to 0.3, that's a change of plus 0.09. Okay, and as I mentioned earlier, we're just going to set up a proportion. So 2 is to 10 as x is to 0.09. Now the reason we can set up a proportion here is because we are using linear interpolation. If we had another different kind of model, this would not work. Solving for x, cross multiply and solve, we get 0.18 is equal to 10x, and x is going to be 0.018. Now, that isn't our answer, right? Because x represented the amount of change. Now r in total is just going to be, well, we have to start, this was adding whatever, 2.21, so I have to do 0.21 plus 0.018. Okay, and when I do that, I believe I get 0.228, and then adding our units, milligrams per minute. Okay, and again, this part isn't extremely vital, but it is useful. Okay, fourth way to represent a function through a table. Okay, so in summary, we have 4 ways to represent a function: numerically, graphically, algebraically, and analytically. Okay, join us for the next video.